The advantage of giving your talk on slides is I sleep well the night before, and I don't even have to think about what I'm saying. I will probably forget. So once at the ICM in Hyderabad in 2010, the worst talk of all was given by a guy who had his slides prepared by his graduate students. He hadn't reviewed the slides. And every now and then, in front of 4,000 people, the guy would say, "Oh, where did that come from?" That was Stan Osher, for those of you who know the guy. Anyway, I haven't.
I was going to say, it's good that you didn't mention it.
Right. So basically, this is a very, very elementary talk. I assure you this is true. I was happy designing the little sign there. It's a report on work in progress. That'll become clear as time goes on. Part of it is a report on work with Tom Hales, oddly enough. Nothing to do with, he and I are working on something that has nothing to do with beyond endoscopy, but somehow the same calculations that I do for this talk also came up in work with Hales. So here's an outline. I'll explain. So I start with a very classical question about representation theory, and at the end I'll relate it to what Chu was talking about this morning. So you'll have to postpone. If you're interested in basic functions for Winburg-Mannheim, you'll have to wait until the end. But you'll just have to assume, you have to believe me when I say that the classical question about representation theory has some relation to it. So it's a question raised by Bob in one of his papers. He asks how to decompose symmetric powers of irreducible representations of GL2. And so the question is very simple. You look at the standard representation, and it's been already mentioned a number of times. You look at the symmetric power of that. It's irreducible of dimension k plus 1. You have a formula for its character in GL2. And you can ask, what's the decomposition into irreducibles? As we'll see later, that has some possible relation to the trace formula. But in any case, as Langen's remarks, you don't really want, as far as we know, when we don't really have any, as far as I know, and there's no explicit example of how to apply this to the trace formula, but the basic idea is you don't care about the exact formula. What you care about is what happens as m goes to infinity. So you fix your representation, and you look at symmetric powers of arbitrary high degree, and you ask what happens to that as m goes to infinity. We'll see there's a very simple answer for that, extraordinarily simple answer.
Is MK?
Yes, as m goes to infinity. Yes, yes. There's another. Actually, interestingly enough, there's another answer as k goes to infinity, and the answer to that is central limit formula. To give you an idea of how simple everything is, it turns out I couldn't believe what I was looking at when I finally started drawing the right graphs. I'm just looking at the normal curve, and I couldn't believe that that's what was happening. I couldn't. Where the heck does the normal curve come from? But I figured that out, and that's what I'll explain today. So the first example, just to put you on solid ground, the first example, and the one which Bob mentioned himself, you look at sigma 2. So that has dimension 3, and if you decompose it with respect to GL2, you get a very simple form. So it's sigma 2m. The determinant factors have to be added because it has to restrict the restriction to the center. So you just get a decomposition like this. It depends on whether m is even or odd as to what happens at the end for obvious reasons. But it's a very simple thing. It's not irreducible, but it has a very simple decomposition. It's very easy to prove, which I'll just mention because it's the only example that's easy to prove. If you have a basis, so it's three-dimensional, and these are your weights, then the weights correspond to partitions of m, of Sm correspond to partitions of this, because you get monomials in these vectors. And you sort these by the value of A0. So you fix the middle thing. And then the other two outside ones correspond to partitions of m minus A0. And you just arrange them in a nice order. So you arrange them so that A0, so here's A0 equals 0, here's A0 equals 1, here's A0 equals 2, and so on. You arrange them like this, and then you just pick off the weights. So this corresponds to sigma 6, and this corresponds to sigma 2. And that's exactly how the proof goes in general. It's very easy to see. The combinatorics is very simple. Bob had trouble with sigma 3. I have a feeling that's why he mentioned sigma 3 this morning. Is because you'll see in a moment why it's easy to get confused about sigma 3. I like my spelling. That's very nice. That's
seems you're also having trouble with sigma 3.
Yes. Yes, much less simple, I guess, is the way to say it. So sigma 3 is not as easy as sigma 2 by any means. In fact, it's very interesting, actually. So my first reaction, as soon as I saw this remark of Bob about sigma 3, I thought, well, let's compute a few. So I have a lot of programs dealing with Coxeter groups and semi-simple decompositions and so on. So I just started programming sigma 3. And we'll see, it's kind of interesting. So let me, well, I tell you here how to actually write the program. I think I'll just skip that part. We can come back later if anybody has any questions. In general, I have a whole bunch of programs that classify. So if you give me an irreducible representation of an arbitrary semi-simple group, or actually even reductive of certain kinds, then I can decompose its symmetric powers. It's hideously slow to do this. I don't know any fast way of doing it. I've thought about various tricks. On the internet, there are various programs that do this, but all of them fail for quite small degrees. Anyway, I didn't need to, because as soon as I did enough calculation, I saw that there's some very simple answer. So I'll give you some special notation to explain what happens. If sigma is an irreducible representation of GL2, I can forget about the determinant factor somehow. That doesn't enter in the calculations because it's sort of obvious how it works. So I take a special semi-simple element and I look at its trace, and I define that to be the trace polynomial. So it's just a polynomial in Q. For example, the trace polynomial of sigma k is just this, which is equal to this. And as I say, once you know that, you know the rest if you know the central character. Okay, so I'm now going to exhibit a whole bunch of trace polynomials. So the trace polynomial is a very nice way. In fact, once you start doing this, you see it's a necessary way to encode the way things work. Without the trace somehow everything turns out to be algebra in a polynomials in some way. So to give you a feeling for how things start, the highest weight of Sm sigma k is Km, and all components will have the same central character. So the decomposition looks like this. And the trace polynomial will be this. And if you multiply the trace polynomial by 1 minus q, you get this. And so if you know the trace polynomial, you recover the decomposition polynomial just by multiplying by 1 minus q. And then you truncate at some point to get the decomposition. So it's very important to keep in mind that somehow there's a trade-off between the decomposition polynomial and the trace polynomial. They're equivalent. For an arbitrary group that's also a semi-simple, well, reductive group, it's the same. You have the Weil character formula, and you're multiplying by the denominator of the Weil character formula and then performing some truncation on chambers.
So just go back, on that previous slide, there's no content here because the CIs are the multiplicities, right? This is just saying how we'll find the multiplicity?
I don't know if there's no content, but there's very little content. I don't know. I wouldn't say it's exactly 0, but it's certainly very low content.
But this isn't a formula that I could do anything with until I knew the CI.
Correct. Okay. No. In fact, right. Exactly right. Exactly right. That's certainly correct. There's no information, if you want. But then mathematics doesn't tell you. I mean, the whole point of mathematics is there's no information content anyway. So. No, I mean, in the traditional sense, information is choosing one item out of a random sample, but mathematics is not a random sample, so it's all determined. God chose it, and we're just following some path that's set out. So here are the decompositions, and these work very simply. So S1 of sigma 3, so the weights go along here. These are the highest weights. So sigma 1, S1 of sigma 3 is this because that's weight 3. Let's go 2, 4, 6, 8, 10, so on. And sigma S2 is this. We know that because this is 6. This is 6 minus 4. That gives the decomposition I gave before. Okay, and now I should mention as an aside that sigma 3 of S3 of sigma 2 is the same as S2 of sigma 3. It's a formula due to Hermite. I learned this in the it took me quite a while to learn this.
Why did the Hermite look at that?
I do not know. I have actually looked at Hermite's paper. I downloaded it from the internet, which is freely available, but I haven't actually looked at that particular part of the argument.
And that goes for M and N?
Yes, arbitrary M and N. It's called Hermite reciprocity. It is a beautiful fact. I learned other beautiful facts too, which you will see in time.
Yeah, I was about to say, I gave it as a homework.
Hermite would be happy, I think, if you did that. Okay, so here's sigma 3 of S3 of sigma 3. That looks so you can sort of see it looks kind of random, but there's a certain pattern, but that's completely broken in the next slides. So now things begin to pile up a little more complicated way, and I think Bob probably got this far in looking at the decomposition, so he sort of got a little discouraged. But again, if you just run your program, and I'll show some version of this a little bit later on. Yeah, this is weight 0.
So S12 gives it to you. S12, the one below it,
What about it?
gives you the 0, gives you the trivial representation.
Yes. No, the trivial representation, yes. That's exactly right. So it grows, so this is 36. You can see how it grows. It grows multiples of 3. So as you keep going, it looks kind of, at first it looks kind of chaotic, but actually after a while you notice that there are many, many obvious patterns. So it looks nicest if you start at the right. So if I start at the right, it's just translating. And as you translate, new things appear. But it's always the new things are the old things. So there's a repetition of length 6, 1, 2, 3, 4, 5, 6. And then it goes again, 1, 2, 3, 4, 5, 6. So it just keeps repeating 6 until it gets to the high point. And then something else happens. So, and the something else happens 1/3 of the way, invariably. So it looks, but if you're doing it by hand, which Bob apparently was, you get kind of confused, right? It's just not, until you start doing industrial scale. Huh?
Are you sure he's doing anything at all?
I can't hear you.
Are you sure he was doing anything at all?
No, but I can find a witness. I mean, if you want to comment on what you did for Sigma 3, I'd be happy to know it.
Never doing anything at all.
No, you have several paragraphs where you talk about it.
Oh.
You forgot that. and then you conclude with a statement, it's no read to continue further. There's no.
Is there 1/3 the way or 1/e the way?
1/3. Yep. And in fact, after a while, if you study, you can see a repetition. So here, it turns out, it's not immediately obvious from this, but it's clear there's some sort of periodicity of period 4. So there's still some repetition of this. So all in all, what happens is you can make a guess as to what an explicit formula is in this case. So I'm now going to show you industrial scale pictures of what goes on. Yeah, so I have to. So yeah, so the first pictures won't make a lot of sense, but after a while they'll look more familiar. Whoops! Oh, this is not working. Okay, so hang on. No, it's the machine. Here we go. Rotate view, full screen mode. So these pictures so I do all the cases. So now these pictures are basically the same as the previous ones, except that I've pushed them together. So in the previous ones I skip because the weights go down. There's a parity consideration. So the weights go down 0, 2, 4, so on as I read from the right. But that's clearly a waste of time on the computer, so I condensed those. So what you're looking at are the same pictures we saw before, but with that condensation factor. So you can again see the repetition of order 6, 6, 6, 6, 6, and so on. It goes to the top, and then you get something nice, and then it goes down the other side. And something a little bit weird happens, as I say, there's some periodicity of order 4, which you can sort of see here, but it repeats like that. There you go. So something really nice is going on. So it's really, so you can get an explicit formula. I can prove it, but the explicit formula is not nearly as interesting as what happens as you let m go to infinity.
So would it be easier to do sigma S3 of sigma 256? I mean, is that easier to compute than this? Or you just had a program for?
On my, so let me explain the programming situation. Originally, I just used a generic program for computing symmetric powers given a highest weight. And that's hideously, I mean, you get billions immediately. And sometimes I would run my program. For G2, it was already hard. So if I wanted to look at, say, S28 of sigma 7, it would take many, many hours on the machine. I'm not worried too much about efficiency at this point. But then I found a formula, and then the formula computes this in milliseconds. So it does take longer as m goes up, but not a hell of a lot. It runs very quick.
Are the 3 and the 3rd related? Or is that just numerical?
No, it's 1/3 all the way through.
But even if you change sigma 3, it's
Yeah.
okay.
Yep. Yeah, so let me say, there's a generic, we'll see later how, there's some secret hidden in these pictures, which I'll explain later. But the general appearance of the pictures is not surprising because there's a notion of something called a vector partition. So vector partition, I don't know how to describe it. I have some other slides, which I'm not showing you today, where you take a bunch of vectors which are contained in a lattice, and you add those vectors together. And then you count multiplicities. For every point that's hit by these sums, you count the multiplicity. And that gives you a distribution on a cone of integers. And that's called, those numbers are, that function on the cone is called a vector partition because you're partitioning the vectors according to other vectors. And there's a general theorem, very beautiful theorem due to Bernd Sturmfels, as far as I know. I don't think there's any predecessor to that, maybe 1970 something, where he tells you that every vector partition function is locally a polynomial, in this case a linear function, plus or minus some little perturbation which depends on congruence relations alone. This is called a quasi-polynomial function. And so there are many other places in this business. I have lots of computations relating to basic functions and monoids and so on, and they're all vector partition functions. Sometimes it's very hard to figure out what the polynomials are, and much less the congruence relations. But in general, you always expect some nice asymptotic behavior because the congruence relations are a fixed congruence, so to speak. So you generally expect some linear thing.
What's a quasi-polynomial?
It's a function which is, you take a polytope in Euclidean space and you divide it up into a finite number of regions, convex also. On each convex region, it's a polynomial plus a small adjustment according to congruence conditions. A finite number, yeah, congruence conditions. And so that's what you see here, certainly as quasi-polynomial. Okay. Okay, so hang on, I have to adjust. No. I can't. There we go. Okay. There's some little trick I haven't figured out yet. Okay. Yep. Okay, so, well, here's just a rehash of what the last pictures showed. And if you look at this, you start reading it, and as I say, there's some periodicity modulo 4, which is indicated here. You can write out an explicit formula. So it's kind of messy, because you have, what you have is, this is the linear part, and so I and j are variables in each one of the two regions, and then you have the congruence part here. So basically, you have a linear part plus a congruence condition, linear part plus congruence condition. So that's what you always expect. It's sort of, these look sort of random, and in fact, I think that's true. In some sense, these are kind of random. We'll see later. There is some formula, but anyway, so sigma 3 is not impossible to figure out, but it takes a certain amount of guesswork to calculation and guesswork. Okay, I say this is a conjecture, but actually it's a theorem. I'll indicate later how to prove it. It's not much use. I don't know of any formula. Well, I show you an explicit formula, but the division into a explicit representation is quasi-polynomial. I don't know in a nice way for arbitrary k. But I think that's not important. So we can at least begin to understand this. So we have what I call, let's look at the general situation. I'm decomposing sigma Sm of sigma k, and as I recall, I can write it like this. And then I have what I call the decomposition polynomial.
Reversed order using your counting multiplicity.
Yeah, so I have to say, I've done this so long and so many times that I reverse the order without thinking about it. So this is the reverse order. So in my graphs, I start at weight 0 and go up to the highest weight. But when I write the decomposition polynomial, I start with the highest weight and go down because that's obviously the stable way to do it. You get a stable condition if you do that. And so, for example, now I write it in reverse order. So I have the same data I had before, but I'm writing reverse order, and you can see it just stabilizes. The initial part of every one just more or less stays the same. That's a basic property of computations of even the basic functions that Chu talked about. Not completely understood in all cases, but apparently there's some geometric reason for this in terms of his sheaves, which I myself don't completely understand. But there's also calculationally, it's very suggestive. Probably this always happens. And it tells you probably in arbitrary cases there's something really nice going on. So what this suggests is, for example, that you're really looking at the tail end of an asymptotic series. And it's almost a geometric series, but not quite. And if you sort of fool around a little bit, you wind up with a it's actually, this series is actually this series. And again, that's a basic fact which probably tells you what happens in all cases is yeah. So we can see more or less what's going on is we have a formula which starts out, if I look at the high end, which is always a good thing to do, you're just looking at the leading terms of that expansion. So it turns out there is a formula. I didn't know this, but it's maybe in Fulton and Harris as well. Is it in Fulton and Harris? I learned it from Goodman. I learned it from Goodman-Wallach. No, much better. It gives you an explicit formula for the weights of sigma m, SM sigma k.
I haven't come to that point in my class.
Just for GL2. So, yeah, I found it in Goodman-Wallach book. I think it's a part written by Goodman, so it's extraordinarily clear. The reason I think that is because I wrote to Wallach and asked him if he knew anything more, and he didn't know anything about it. There could be many reasons for this, but anyway, it's very pretty and it's explained very nicely there. There is a classical formula exactly. Before I tell you what the formula is, I have to, formula for the trace polynomial. But as you recall, the trace polynomial, you get the decomposition you get just by multiplying by 1 minus q. So the formula is for the trace polynomial. And of course, you have Weil's character formula, but that isn't quite enough somehow. You want something very explicit because you want to be able to factor it. It turns out that factoring is what's important. And it's this SM is not irreducible, so it's not, I mean, it's a sum of Weil character. Anyway, there is a very nice formula, and it's very simple to derive. So you have to know what the Q analogs of some familiar functions are. The Q analog of the function n is just sum of Q powers of, n powers of Q. Then I have n factorial Q, which is just the product of these. And then I have the combinatorial, the Pascal's triangle, which is just that. And this has many different representations, all of which are very useful to keep in mind. And if I set Q equals 1, I just get the usual things. And this is also written by, just to remind you what this is, it fits into a nice Q analog of Pascal's triangle. It's extremely beautiful, but very simple stuff. Oddly enough, I think it's due, well, Newton and Gauss, I think, are the really progenitors of this. I'm not sure exactly. I've looked at various papers of Newton where he sort of talks about things like this, but the Ur version, so to speak, that I know of is in Gauss, where he's looking at theta functions. And he's very interested in similar functions to this because he's looking at theta functions. There's some relation to quadratic reciprocity, which I don't really know very well. But the point is that the same rule applies here, that this term is equal to this term plus this term and some extra factors of Q, which I state. So we have classical formulas. It's symmetric in K and n minus K. The top row is always very simple. And then you have the induction formula. And then I don't see any way to see otherwise, except by using these things, that it's a polynomial in Q. We'll see later that there are combinatorial interpretations, but the combinatorial interpretations are through representation theory. And in fact, I have to say, for a long time in my computations, I tried, in a sense, when I start looking at my formulas, it seemed that what I wanted to do was understand a different proof of why this is a polynomial in Q by actually factoring out. I mean, with this, you can see where primes appear and start canceling out primes and so on. I couldn't see any easy way to do that in that case. It's a mildly interesting question. Anyway, the point is that because of well-known dimension formulas, it's not going to surprise you too much. The trace polynomial of this is this. Because if I set q equals 1, I get the dimension of the alternating power. And the trace polynomial of that is just that. So we know we have an explicit formula for trace polynomials for important representations of GL2. As far as I know, there is no generalization to arbitrary groups. Known. I have many computations which suggest that, in fact, well, for low rank and low dimension, that there is such a formula. And for GL3, I have some simple cases where there is actually a formula for such things. But it doesn't tell you what goes on. What it does tell you is when you start computing more, you can see that, I don't know how else to say it, there's a little element of chaos that appears. So things start to make trivial sense, but it just becomes more intriguing. So I would bet a great deal that there are such formulas for higher rank groups. But at the moment, I have no, except in very small number of cases, I have no formula for it.
This looks great, but in order to use this, you still need coefficient by coefficient what the expansion of this is in terms of q, right?
Yeah. Are you complaining?
Oh, no, just an observation.
No, in fact, no, when I have to say, when I first saw this, in fact, even in writing, I say it doesn't seem like this tells you very much, but then I kept on working, and eventually I saw the light. So there is light to be seen.
So, can I ask, what, if any, is the difference between a weight-compatible bijection of bases?
I'm sorry, I don't understand.
What's the difference between, you said, a weight-compatible bijection of bases and an isomorphism?
Well, it's the same as what I did for SK of sigma 2. I just picked off the weights. But those weights I pick off are by weights. There's no subspace of vectors corresponding to the decomposition I give you. In other words, there's no so I give you a proof for sigma SM of sigma 2, right? In which case it's sigma 4 plus a sigma 2 something minus something minus something. And I gave you a proof of that because I can pick off the weights of representations of GL2. But the isomorphism, if you want an explicit isomorphism between that and that, it's much harder. The weights are not trivial. It's not.
It implies there's an isomorphism, but it doesn't give it to you? Is that
It says there, yeah, the weights I pick off are not a stable subset under GL2. It's just a weight. That's what I mean by a weight-compatible decomposition. So you can, GL2 is very nice because you can pick off the weights very easily from the highest weight representations. But that doesn't mean you're actually picking off GL2 stable subspaces. Okay, and these are very easy to prove. The first is by induction, just using the basic fact of this is equal to this plus this with a Q factor involved. But the second is just somehow a little nastier. These are proven in Goodman and Wallach by a slightly different, they have a different way of proving it, using Mullian's formula actually, which is probably what your homework exercise does, if you get around to it. So anyway, these are elementary facts, and they have very, very nice proofs actually. And they're well known. I did not know them until I had computed. So I started computing a huge number of these things, and I conjectured something like this formula, only not in such a nice form. I had an equivalent version, and I was astounded to read in Goodman Wallach that it's been known since the days of Frobenius, probably, something like that. But it's not easy to see. If you look on the internet, you'll find all sorts of discussions where they clearly don't know the formula. It's just not a really well-known fact. Okay.
Sometimes one can relate exterior and symmetric power by using super vector spaces.
Yeah, you might want, I was wondering, I've already actually thought that maybe something like that, maybe we can talk about it later or maybe if you answer your email. Do you answer your email? Good. So I wondered about that actually. It's exactly something that occurred to me, and I suspect and if so, then in higher rank it may actually be an important fact. So for this case, it's easy enough to see otherwise, but I suspect it's something like that because I've read one of Bernstein's papers on supergroups. Okay. So I'm just recalling basic formulas here. Now, the way I can write this, it happens to be useful to rewrite this. So I can write the trace polynomial like this, and I write it like this. So I think what's going on here, I'm pretty sure actually. What's going on here can be, if there is such a generalization to higher rank groups, and what happens here is I get a sum over all the Weil group all the chambers, and I get some, there's some sort of Weil version of the Poincare dual of a polynomial, depending on which chamber you're in. I think this is a familiar technique, a familiar fact that appears in computations in Weil groups. So that's just a fact. So you get some simple formula, and this is the decomposition polynomial. So before I said you get the decomposition polynomial by multiplying by this and then truncating, and this tells you exactly why that works. There's no overlap somehow in the middle. It's a simple fact, but I think it's fundamentally important. Anyway, I've said this. This is a different version. I just ran out of space on the page before. And so now let's look at it more explicitly. So let's just check how it goes with Sm of sigma 2. Well, in this case, I can actually do what I said I didn't want to do. I can actually match up. If m is even, then this divides this, and so on. So you can actually write it out. It already becomes quite hard for sigma 3. And in general, the congruences you have to match up are order of n factorial in the denominator to get all the congruences to work out. There's no easy way to see what's going on. I suspect there is something, but I didn't have to deal with it. Yeah, so as I say, you can see that although we know exactly that this is a polynomial, it's not easy to see the general form of that polynomial. So my initial thought from this was, oi, I don't want to deal with it. But we'll see what happens. So we can already understand part of the conjecture. I've said that up to 1/3 you get this Taylor series of this, and you can see now why that is, because you modulo 3m plus 1, you're just going to get that. So you can see immediately that at least we're in good shape, because we do see why we get the leading terms in the decomposition polynomial the way we do. And actually, you can prove the conjecture. I'm not going to prove my conjecture. Remember, I had a formula that I conjectured for sigma 3. I'm not going to prove it, but once we know that you use the same Pascal's formula to get an explicit formula, and then it's an induction proof. Kind of messy, but it does give you something. This is the recursion you use. Okay. Okay, well, let's look at some more examples. I mean, I love to compute. Above all, I love to compute. So, and I have this whole assembly of programs which just I love. And I just, so I can't, I mean, I just love to do that. So here's sigma 4. And again, it starts off a little too nicely, but it quickly looks a little worse and worse. But again, it's messier than sigma 3, but again, you don't lose hope. It's not depressing. It's some alternation. I have to say, I don't really understand quite why this works. So in this case, the congruence relations seem to be modulo 2, and not quite modulo 2, and probably modulo 4 again, something, but I don't understand quite why it alternates so strongly. I don't have any, but I don't think you need to know that. Yes, that's exactly what Sturmfield's theorem will tell you, that I don't think Sturmfield's is quite so precise, but subsequent, it's bounded. It's a congruence. It's really a fixed congruence relation, a fixed congruence polynomial.
Sorry, what's bounded by Sturmfield's is the period, right? What's bounded by Sturmfield's is like the period of the...
No, what's bounded, no, it's a fixed, you add and subtract the same thing, which is bound. In other words, you have a finite set of polynomials, and those have lower order than the basic polynomial. In other words, you have your polynomial, locally polynomial, so you divide up into regions. On each region you have a polynomial, and on each region also you have a set of congruence conditions and some I don't know, correction polynomials. And the correction polynomials depend only on the congruence, and their degree is less than the, so it's really quite a strong theorem. Now, again, when I started this, and I'm still not through with that, because for higher rank groups you get enormously more complicated things to deal with. But in those, there's a huge literature on this, on vector partitions and Kwazii polynomials and so on. I found it all rather depressing, because there's clearly no one answer that works all the time. It's very, very complicated. I think in these calculations, I suspect there is, in the end, a really nice answer. But then, you know, Coxeter groups are really nice things, so not too surprising. Okay. And now I'll show you some more slides, if the machine likes the idea. See, which ones am I looking at? Oh, 814, yep. For some reason. No. Overview? No, it doesn't. How do I?
I think view is the right one.
Yeah, it doesn't. I'm clicking on it.
Really?
Yep.
Do you have an F11?
Control.
Control F.
Function
Nope.
F11.
Control F gives me nothing. No. Oh, Control. Oh, F11.
No, F11.
No. Ah, what'd you do?
Control L.
Okay, got it. Okay. So again, the first few steps look kind of ugly. But so again, I compressed because of the parity condition.
There's always a single peak, isn't it?
Well, yeah, it's really, as I say, I don't really understand why you get this very simple oscillation in a sense. But it's like congruence conditions piled on congruence conditions. In fact, I don't know if that makes any sense in Sturmfeld scheme, but it's certainly something like that here. And here we go. Here we go. Sorry, I didn't go any higher. But there are encouraging things about this. So it's clear. I was a little bit worried before. It's not quite clear that Sturmfeld's theorem applies in the strong form to this. So I was happy to see that the...
You know the shape of this exclusion?
Yeah, I do. Can you guess what it is?
It's not a Gaussian.
It's the derivative of a Gaussian. It's not quite, that's not quite right. But as k goes up, you get exactly the same shape approaching the derivative of a Gaussian. At first I was very mystified by this, but then I'll give away the secret. Multiplying by 1 minus q in the limit becomes the derivative, if you scale it right. And so you can see what you hope to happen in general. The denominator of the Weil character formula becomes a differential operator, an anti-symmetric differential operator. And I have much evidence that again you get something like at the end I'll state the exact conjecture and a theorem for GL2 and a very weak conjecture for higher rank groups, but that's what's going on. You're applying, so to get from the weight polynomial, from the trace polynomial to the decomposition polynomial, you're applying this differential operator. So I've never seen anybody do that. And I looked through the literature. I've never seen many papers of Steinberg dealing with the denominator and the differential operators and so on, but I've never seen anybody apply it to anything like a Gaussian.
So here you get a smooth curve and not a singularity like before?
Well, you get this. This is, I mean, I can tell you, no, it's not smooth. It's piecewise polynomial. And I know exactly what the polynomials are. I will tell you that at the end. So,
As k goes to infinity, you get smooth.
no. As m goes to infinity, you get a piecewise
No, but I know. Like when you fix one of the guys and you go the other way, it's piecewise. What if you just move them both?
I never thought of it. Well, I mean, I don't know. It doesn't seem like an interesting question, but no. No. I mean, but what I can tell you is, so what this is, so before I had a piecewise linear function, and now it turns out to be piecewise quadratic, in 3 pieces to be exact. Okay. And you'll see why I'm happy on the next slide. No, it doesn't. Why doesn't, see, it's somehow it just doesn't want to, yeah.
Before you had 1/3, what is analog of 1/3?
It's 1 over k.
Which one?
I want to open this one.
Right, click on that.
Oh,
Yeah.
why
Yes, you just have to click on it and then Control L. That's it.
okay, yeah.
Click on the tab
But
and
but
Control L.
but what you didn't see is that when I click, sometimes it doesn't work.
Okay.
I'll let you think about it. But
Okay.
as long as we just keep clicking, sooner or later it'll open up, and that's all right. So again, the same thing happens. I try sigma 6. But this case, you just see the end result. I won't take you through the animation. So, so again, you get something very, it's certainly something's going on. Right? I mean, the curves, what you can see is that the curves look very similar. The k's are different. They're similar, but not exactly the same. If you overlay them, you can see little differences and so on. It's more and more the derivative of a normal curve as k goes up.
Yes, but at of a given k, is it ck differentiable? Is it k times differentiable?
Yeah, it's the sum of them. It's two. It's degree 2 for 4.
That's
I think.
what they say. But you go from one polynomial.
Oh yeah. No. Yeah. So you will see. So I have an exact formula for these, and you will see that it works out that way. Okay. Yeah. At first I was really worried. I'd have to find derivative, blah 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 blah. But no, there's an exact formula, which is very simple. So let me go on. Oh, here we go. Full screen. No, it's not. See, it just, I mean, you can't see, but I'm clicking on the mouse and it's not registering. Is it just slow? Yeah, it's just slow. For some reason, the microprocessor somehow,
Okay.
it's just slow.
So instead of doing that, all you have to do is just hit Control L.
Oh, yeah, that's, I'm sorry, you told me that and I forgot.
Okay.
Very sorry. Okay. So, well, I'm doing all right. I have 13 pages to go and a few slides. So, as I say, multiplying by 1 minus q just does this. So basically, if we scale things all correctly, it just becomes the derivative. And this suggests, instead of looking at the decomposition polynomial, I should go back to the trace polynomial. And so I won't show you quite as many examples, but I'll look at the final version.
And then Control L.
Yep. Yeah, I gotcha. There we go. Beautiful. So now I actually, after some work, I said this looks really normal, like a normal curve. What you can't do is prevent me from losing the pointer. Here. Okay. So again, I just look at some. So this is the the blue is the normal curve, and this is its derivative. I have this here only to remind you of what the previous curves look like, so you can convince yourself that something's going on. So I only did it up to 32 because I didn't see any point after doing this. And it's not quite a normal curve, and as I say, I know exactly what it is, and I know exactly why it's not quite a normal curve. But it's clear I'm onto something, right? It's clear that there's something really interesting going on. I expected something really, really complicated. But I'm now pretty excited, as you can imagine, because I love to compute, and I clearly have more computation to do. But I'm beginning to get worried because I have lots of computations and not so many theorems. But in fact, I figured out what was going on. Okay. So this is just to remind you, it's the normal curve versus its derivative. So what we've been looking at all along are things like the derivative of the normal curve. And then I do this. So Control L. Okay, so it looks very much as though the trace polynomials have something to do with the normal curve. And at first I was really hopeless. I thought it was terrible. So what's remarkable about this is if I do a very similar problem, I take an arbitrary irreducible representation with a highest weight lambda. And I look at the weight decomposition of pi n lambda for as n goes to infinity. So lambda is the highest weight. I look at the representations with highest weight n times lambda. And I let n go to infinity. Then this is known to be a vector partition function. And there's an explicit formula due to Gerrit-Heckman, which applies in every case. And it's very complicated. So you have these regions. You divide up Kwazii polynomial, blah, blah. Heckman has a very natural formula for the polynomial part. Not for the congruence relations, which are rather random, but for the polynomial part, there's a very nice formula. There are many different ways now to understand how it goes. It's basically you're taking a direct limit, you're taking the, what do you call it, when you take a measure upstairs and you push it downstairs. And that's the kind of measure you're looking at. And it breaks up in polynomials for various reasons, because the projecting region breaks up into a certain number of regions. So there's a very nice formula. It's elegant, and it's very it's conceptually very simple, but very complicated in actual practice.
Upstairs, it's a very clean thing. Before you project, it's clean.
Yeah, but Fourier projector is very simple. It's only, well, except the fact that it's a polytope of some complication. So, yeah, it's a very beautiful formula, no question about it. But the behavior here is much simpler than what you see in Heckman's formula. I don't know how to explain that, but in higher rank, it becomes clear that somehow and still Heckman's formula is somehow sitting in here in some funny way, because there are many cases where you wind up looking at it. But in those cases, it turns out Heckman's formula is simple. So what looks to be is that the symmetric powers are much simpler than just multiplying the weight by something. I cannot find any trace of this in the literature at all. As far as I know, I'm the first person to actually do industrial scale computation of symmetric powers. I don't know why. And as I say, for higher rank, I don't have, I mean, my programs are hideously slow. So if I can't find out what's going on for SL3 or SP4 or G2, I'm in bad shape. If I can't actually make a conjecture based on those data, I will commit some form of seppuku. Huh?
Which group do you have data?
Those three. I have, for higher rank groups, I have data for SP4, SL3, and G2. And it looks promising, but I don't have a formula. I don't have a conjecture yet.
Look different? You look different or not? You don't get this Gaussian bit?
It's not a Gaussian. I mean, it's something like a Gaussian. It can't be a Gaussian. So I'll say something later, but it'll make it more plausible. But in a word, what I seem to have is suppose I have a highest weight lambda. I decompose it into a sum of fundamental weights. I look at the representations with fundamental weights. I look at those symmetric powers. I get a function on the convex cone of the hull of the vial orbit. And that's my base data. So I start with that. If lambda is the sum of these things, then I just take the convolution of those. And that seems to be, I don't have enough data yet to really say that's what happened, but that seems to be what's going on. So I've never seen anybody take convolutions of vial hulls of things, but it's.
You take convolutions of anything, they become Gaussian.
No, it's not Gaussian. It's not Gaussian because it's vial invariant.
But then it's
It's kind of Gaussian. If you call it, I don't know what to call it, but yeah, it's not.
there's a theory if you take a lot of convolutions.
It's a kind of Gaussian, yes. It's a kind of Gaussian.
Universal behavior which is an infinitely
Okay, we can.
distribution.
Do we do your email too? No. So I can.
Yeah, what do you mean? You emailed me.
Right. Okay. So yeah, I mean, I think that's right, but I don't have enough evidence quite to but that's my present guess based on what I know. So.
Am I supposed to stop you?
It's okay. So.
Am I supposed to stop you?
I have till almost 3 o'clock. No, I mean I have till. I mean nobody has kept to the 50 minutes so far. Okay. I mean basically I just told you what I have to tell you, except that. Except that why it works. So I actually know how to prove. I can actually prove this statement for GL2. So the reason is you're not going to believe this. So we know this. I have some sort of thing where I know how the leading terms work. It's a Taylor series. This works out. That's pretty clear. And this so now I say I believe I can show, but actually I should have corrected that. I actually can show. And the reason is because what happens is that what happens is m gets large and k remains fixed, the m sort of becomes m, and sort of the whole polynomial looks like this. I mean, you have all these powers of q, right? Q to the m plus 1, q to the m plus 2, up to q to the m plus k. But as m grows, they all sort of compress together. So what you're looking at is this. But this is just a binomial distribution. And that's exactly, so what you're getting is exactly the binomial distribution for the sum of k independent variables of a certain range. And those are the local polynomials you get. So you can predict exactly what the function is, smooth as Pierre wants. And it's very simple. And its convolution agrees with my convolution conjecture. So what you're looking at exactly are the convolution. So what this is the convolution of unit intervals. And that's exactly what you get. So I say conjecture, but actually I'm pretty sure, I haven't written down the proof, but I think I know how to, there's some version of all this I'm not telling you, which actually you can put it in an because you can see exactly what happens asymptotically. Now, I have no minutes, so I won't tell you. But what this implies, so I recover some of what Chu said this morning. But what I can do is, his question is how to compute the basic functions. Because the Satake transform of GL2 is so simple, once you know the decomposition of symmetric powers, you can calculate the basic functions extremely explicitly. And so once you know the decomposition, you do know the basic functions extremely explicitly. And so in a sense, you know, and since you know everything asymptotically about what happens for his functions on the Windberg monoid. And I'm anxious to see what his resolutions tell you about how things work out. So I won't. Well, I should say this. So here's another editing. I should take out the word encouragement and replace it by something a little more savage. But it's the second last slide. So there are a number of things which I work out. So I have computed basic functions for the first really interesting case is GSP4. So for GL2, at GLN, and the standard representation, you know the basic functions immediately because, well, you have it's easy to see there's some formula which should work out because of the irreducibility questions. But for higher rank groups, the interesting case is SP4 when I know, again, to compute the basic function for the standard representation of SP4. And it turns out I have a conjecture. I haven't proven it, but again, I don't think it's too hard. I know exactly what the basic function is. It's very interesting. It's somehow you look at this cone. So in that case, you have a three-dimensional cone coming out, which is square because that's the convex hull of something. And so there's a lot of hope somehow that in the end, you'll have some more or less explicit form of Sturm-Fels theorem for what's going on. All these things are vector partitions. So the computation of basic functions comes in two steps. One, you compute irreducible symmetric power decompositions. And the second step is you apply the inverse Satake transform. And again, there's some hope that both of those are somehow comprehensible steps. Just recently, because of work with Tom Hales, I'm able to generalize this to quasi-split groups. And for quasi-split groups, something absolutely amazing happens, which I was always sort of puzzled by. It seemed like something nice was going to happen, but I never understood. There's a formula. If a quasi-split group gives rise to a semi-direct product of a Galois group or a Z and the Weil group, the Weil group and the Weil group and the dual group, and you're looking at representations of that. And it turns out that when you apply the Weil character formula to that, which is due to constant, you wind up computing the character of a certain very simple split group. You knew that. Huh? Anyway, it turns out that the whole thing, so all the calculations reduce to that. I have no idea how that fits into Langland's scheme, but it's very, so again, I can do all the computations now for quasi-split groups as well without having to rewrite all my programs, which is very nice. So, okay, I'm through.